Hi, everyone. My name is Dean. I've been working part of the security team at Lyft for 5 years, software engineer there that's focusing on infrastructure security. I'm really excited to be talking about this project that we worked on at Lyft. There were many people who've contributed to this project too. I'm just fortunate to be presenting on a lot of people's behalf here. So I just wanted to acknowledge them and also thank them. So while ingress filtering from the internet to your services is very common using firewalls, it is far less common that people are observing traffic that's leaving their services network. It's one of the most impactful things that you could do for your company. If you don't observe and control this traffic, it's a significant risk where if a service becomes compromised, then oftentimes the threat actor is going to potentially exfil data, download arbitrary payloads during runtime, or call back to command and control. So there's a couple of recent prominent hacks that I'm sure certain people have heard about or at this point really sick of hearing. SolarWinds supply chain attack used a backdoor that regularly communicated with command and control through DNS and HTTP. The Log4 Shell, Log4j vulnerability, another zero-day all-hands-on-deck type of event where everyone wished they had some sort of egress filtering during this time. So when exploiting these types of vulnerabilities like Log4j, attackers often still need to make an egress call to download additional payloads or to exfil data. So being able to control this egress traffic can directly help mitigate 0 days like this. So why is this difficult? Why aren't more people doing this today? The first call out, it's people, it's organizational. You need to convince the decision makers that you are going to now funnel all your traffic through a proxy, a single point of failure, and that the security benefits of doing so will outweigh the risk of this single point of failure. So now you need also this team to operate this mission critical proxy. It's high stakes, right? At Lyft, this was a bit of a culture shift for our security team because we weren't known historically for operating these mission critical services, and we were the ones building and driving this initiative. We have a culture where if you build it, then you have to operate it. So you're really incentivized to make sure it's running well. Our engineers were actually really excited to be taking, and we leaned into this opportunity to do this. So now let's talk about why this is technically difficult. And it really boils down to two things, TLS encrypted traffic and DNS, right? How do you control DNS exfiltration attempts? The vast majority of your egress traffic is going to be TLS encrypted web traffic, HTTPS. Let's talk about that first. A reminder of these are the steps that occur when you establish a TLS connection and HTTP request. So like, let's say we were to funnel this traffic through a proxy, just transparently, and we are not going to be manually middling anything. There's really only a few attributes that we could control this traffic, right? We have IP address available to us. We have the ports. Maybe we have SNI, and I have this highlighted in a question mark because not all clients relay this information, and there's the potential down the line that SNI might be even encrypted. So let's talk about also the options explored that we did at Lyft. So these are things that we explored but ultimately didn't go down. And one of the first things is man in the middle. Let's man in the middle all TLS traffic. So this directly addresses the challenges faced with TLS. So this is where we decrypt everything, and now we can control traffic based on the host name, the URLs, and the payloads if we wanted to. But we felt this really introduced too much risk for us to adopt this option, right? You're essentially breaking end-to-end encryption, and there's going to be a single point where all traffic is being decrypted. Now you also have to worry about managing your own certificate authority, and then how would you need all services to trust a root certificate, and then you need to worry about how to rotate and manage the life cycles of these certificates. So we thought, all right, let's try to keep things a little bit more simpler. Let's just control DNS. All requests make DNS requests, right? We'll maintain an allow list of domains that services are only allowed to resolve. But this doesn't quite work out completely because if a threat actor compromises a service, they could just circumvent DNS altogether, and if they just use the IP address directly. So then we thought, well, okay, let's pre-resolve all the hosts. So we'll maintain two allow lists. We'll have an allow list of host name, and then we'll have an allow list of IP addresses. So we'll constantly pre-resolve all these hosts in the background, sync these to a layer 3 proxy, And if a service egresses out to an IP address that hasn't been pre-resolved, then we're just going to block it. I think this actually might work out in theory. I'm just not sure if it's really practical at scale. So we were actually really close to go down this route, but ultimately decided not to. It just felt pretty yucky, like really messy. So now let's talk about what we did ultimately decide to do. So this was our ultimate design goal at Lyft. We really wanted to delineate services into public and private subnets. We wanted to force all outbound traffic through a proxy, and at Lyft we use Envoy because, well, we built Envoy at Lyft, particularly Matt Klein did, and I don't want to go too many in the details of what Envoy is. There are entire conferences just dedicated to Envoy, and the well is really deep there. But for our purposes, for the purpose of this talk, just know it's a proxy, and it's a very highly extendable proxy at that. So private subnets, they're defined by two nice characteristics. First characteristic is internet egress traffic cannot go directly out to the internet. It must first traverse a gateway or a proxy that lives on the public subnet. And the second nice characteristic is there's no public IP addresses assigned to the service. There's no public interfaces. So you're not a single security group misconfiguration away or accidental firewall configuration away from directly exposing your services to the internet. So whatever you do decide to do to improve your the network security posture of your services, I would argue it should get you one step closer to this model. At Lyft, we use AWS, and it's very difficult just to start with this model because a lot of AWS's services, their offerings, by default will traverse the public internet, right? Like S3, DynamoDB, STS, these all traverse the public internet by default. So Lyft is also a microservices architecture, and we have over 1,000 services at Lyft. And we ultimately wanted to know the individual services that are egressing out to the internet, and because we're not manually milling traffic, we felt that the majority of the value we get is just from controlling the domains that we're allowed to egress to. So we wanted to be really granular. Every individual downstream service is going to have its unique allow list of upstream domains. So we could represent this as a dictionary mapping that we see here, right? So 1,000 services and 1,000 unique allow lists. If a service is intending to reach a host that's not in an allow list, it would just block it. So a quick primer on proxy types. There's ultimately two types of proxies that Lyft uses as the foundation to for its egress restriction. And the first is the client-aware connect proxy, where we wanted services to primarily use. We've been calling this happy path at Lyft, so denoted by this sun emoji here. We want all services to use this. And as a secondary path, we call it transparent proxies. It's just going to be a catch-all. It's going to catch all this leaky traffic that's not obeying the connect proxy. We'll also dive a little bit later. We also have additional levers to control traffic that we do see in the transparent proxy. So client-aware connect proxy is self-descriptive. You may also have the term explicit proxy, and it's where the service or the client knows that there's a proxy sitting between it and the upstream server. So connect is an HTTP method. Majority of y'all probably heard of get and post requests. Well, HTTP connect is just another HTTP verb. And what it is it's an instruction for a proxy to open a TCP connection to an upstream host. As soon as that TCP connection is open, the proxy is just forwarding bytes back and forth. And what this diagram depicts is the steps that a connect proxy calls make. And there's really two important highlights within this diagram that makes it really attractive to control egress traffic. The first important highlight is DNS. You've offloaded the responsibility of DNS resolutions now to the proxy. So this makes it a lot easier to control DNS for your services because now there's no reason for external resolutions to happen from the service. The second attractive aspect is you get this really, you get this nice tuple. You get to see the upstream host that the service is attempting to connect to, and you also get the downstream host that's making this call. So we can inject these, the downstream host as an HTTP header. There's multiple ways you could configure a connect proxy. The first way that that we use at Lyft is we inject these HTTP environmental variables to all our services at Lyft. So if an HTTP client sees these environmental variables, it knows it must first make a HTTP connect tunnel. And then there's also other ways, like you could also divide it in code. So this is a short Python snippet that shows how to use a connect proxy. But the first option definitely is a lot more attractive because it's language agnostic. So just to drive the point home, a TCP dump of a connect call. So this really nice tuple that you're interested in, you have the upstream host that's highlighted in red, apilift.com, and then you have the downstream host name, this basic64 encoded value as the host. So some of y'all might be thinking, or just kind of triggering in your head, like how do you authenticate to the proxy? And it's an orthogonal talk that I honestly can spin to a separate talk, but just for the basis of these talks, this particular talk is just out of scope. But find me afterwards if you have more questions on that. So let's talk about the other path. Transparent proxies, they work by rerouting traffic without the client knowing, and this can be done through IP tables. So IP tables will redirect all internet-bound traffic to a proxy, and it's vastly more complicated compared to the client-aware proxy, and again, primarily due to TLS encrypted traffic and then DNS exfiltration. So once the proxy receives the redirected traffic, it has many ways to route this traffic. So IP tables operates on layer 4 or 3, and once the proxy sees this redirected traffic, if the traffic is TLS, you have the option to allow block on SNI, but there's no guarantee we have SNI. If it's plain text HTTP, we can block route based on HTTP host headers, and then for everything else, you could block allow based on IP. And then finally, again, because the client doesn't know there's a proxy sitting between it and the upstream host is attempting to reach out to, you now have to worry about DNS. So cool. Now we've covered the foundations of what we use, the connect proxy and the transparent proxy. How do we actually use this now in our restriction? So here was the strategy, high-level strategy. This is a 1,000 feet view. Using Envoy, we created an edge internet gateway that contains both a connect and a transparent proxy. So again, the client-aware connect proxy is the primary path that we wanted all services to use. The design is far simpler. The big plus is that we can control DNS for services, and then the transparent proxy is going to catch all this leaky traffic. So it's going to give us the confidence that all traffic is obeying the connect proxy, and if it isn't, we know about it, and then we could spend some time to figure out how do we get this migrated, this traffic shifted over to the connect proxy. But again, there's additional levers we actually do have, which we'll cover in more detail on the transparent proxy side to control traffic. So 1,000 feet view, now let's really dive into the nitty-gritty details. Oh, sorry, one quick thing too is like, if we don't see any traffic at the transparent proxy, we could just block everything at the transparent proxy at that point, and then everything we're confident is going through the connect proxy, so we just eliminate that path completely. So this diagram is lifted directly from our internal tech specs. It's effectively a blueprint on how the internet gateway works. And we wanted all services to use this as their main way of egress. So again, we use Envoy at LIF, and I don't want everyone to get too hung up on Envoy because the steps here are still ultimately what a network proxy needs to do, regardless if you're using Envoy or not. So let's walk through the steps. What happens when a web request occurs? So starting from the left side over here. A service wants to make a request out to the internet. It's going to see these environmental variables injected, so it knows it must make a connect tunnel out to the internet gateway. The connect gateway is going to receive this call, and then it's going to terminate there, and then going to see this tuple of the downstream host that's making the call, in this case, Python example 2. And then it has the upstream host that it wants to connect to. We pass this information into a layer 7 HTTP RBAC filter. This filter has a dictionary mapping of all our allow list. It's going to look it up as the Python example 2, grab the list of allow list, and then if it's in there, allow that traffic. If it's not, we're going to return a 403 and just deny that traffic. In this case, it is allowed. So then we forward it to a forward cluster, which is, in Envoy terms, you can just think of this as a forward proxy, HTTP forward proxy, make the DNS request, and then forward it onwards to the internet. So next, I'm going to talk about the transparent proxy. And this path is how we capture leaky traffic. And also, we have a bunch of levers to control traffic. So comparatively, it is far, far more complicated. And this is the heaviest slide of the presentation, so please bear with me, hang with me in there. We'll go step by step of how a web request goes through. So this is lifted, again, directly from our internal technical documents. And the reason why it's far more complicated, because we need something to extract and preserve the data we need from the calling service and make it available as transport properties to the internet gateway to allow or deny on. So let's walk through the request. We make a web request, and for some reason, this traffic isn't obeying our connect proxy, and we're going to capture it, right? So we IP tables redirect this traffic, and you'll see 1234 gets changed into a local host, and this is a local running proxy living on the same network space as the service. So we have this additional proxy that needs to live local to the service because this proxy needs to be able to preserve this transport property. It needs to be able to restore this destination IP address. And when you IP tables redirect something, this destination IP gets preserved in a local socket called original destination socket. So Envoy is going to read it from the local socket, which is in the same network namespace as the service, and it's going to use proxy protocol to preserve that IP, so it gets added as a header in the TCP packet. We're going to forward this information. We're going to upgrade this connection into a connect call, and then we inject these additional properties at layer 7. So the upstream host name, which is sourced from SNI in this case for TLS encrypted traffic, and then also the downstream PyExample2 service. Now at layer 4 we have these IP address, layer 7 we have SNI and service, and then we forward this to the internet gateway. And at this point, it's very similar to the previous side in how things work. So then we terminate connect. We have the downstream service name, and then the upstream host pass it into our layer 7 HTTP RBAC filters. So yeah, check it against the allow list again. And if it's allowed, we forward it to, we unwrap the proxy protocol, so terminate that to restore the destination IP addresses. And then we forward it to a TCP forward cluster. So I'm out of breath just talking about this. So yeah, I think I wouldn't, it's okay if you fogged out there. Probably take a bit to digest, but the key takeaway is transparent proxy is much more complicated because you need something to preserve the transport properties of the calling service. And we do this with a local running proxy local to the service before we forward it to an internet gateway. So let's walk through things now. If a service gets compromised now and it attempts to reach out back to a malicious domain, if it's using things that obey the connect proxy, we're going to see it. We're going to check it against the allow list, and if it's not part of the domains, we block it. If it tries to circumvent the connect proxy, well, we trap it via the transparent proxy via IP tables, so we block it there. And then finally, if it tries to use DNS exfiltration attempts, they can't use that there because we've blocked external resolves. So rollout. The core team of the project was actually really done by 2 engineers, one of them being me, and configuring the gateway was actually the fastest part. There was no custom development in our solution. Everything was out of the box from Envoy, which is open source. I'm not a C++ Envoy developer. I'm still filing public GitHub issues, reading the open source docs, and searching public Slack channels for help. So standing the infrastructure was the quickest part, and what really took the most amount of effort is how do you now shift traffic through the internet gateway without disrupting production? So fortunately, at Lyft, there's many levers we have. We can onboard by staging versus production versus canaries versus language types. And then finally by tiers, where tier 3 means it's not that critical. If it's disrupted, like no one really kind of cares. But all the way up to tier 0, where if you disrupt that traffic, then you might be affecting, or you will be affecting our riders and drivers from going online. So as we've onboarded services, we just passively observe this traffic, and we use this as the opportunity to hydrate the allow list, like what domains are services reaching out to. And we're just shadow denying traffic, that allow list. So once we see the shadow denies essentially flatline to 0, that's when we switch the shadow to enforcement mode. So this is when we're actually enforcing those HTTP RBAC filters that we saw earlier. And then finally, once we flipped that switch, we really made sure we communicated broadly with engineering. We made sure our infrastructure documentation, our runbooks were really crisp, because when we now see traffic that is denied, service owners will receive a PagerDuty alert. And then within that PagerDuty alert will show like, this is the traffic that your service is attempting to reach out to. It was blocked for this reason. And if this is normal, this is how you correct it. And then if it's not, this is how you reach out to security. Some of the concerns were potential latency incurred by the proxy. We saw an increase of P99 of roughly 10 milliseconds, and this is attributed to the connect TCP tunnel being established. But after that TCP connection was established, subsequent requests were really just negligible in comparison. We collect and monitor a lot of metrics not covered here, but really the performance of the Envoy Edge Gateway is dependent on CPU and the bandwidth available to it. So within our squeeze testing or load testing, we observed that really a high TCP connection count paired with a high bandwidth has a direct correlation of increasing the CPU usage. So we just scale Envoy on CPU. And this diagram is somewhat simplified, but the bottom line is we have dedicated EC2 instances per Envoy node. We wrap this in an ASG, so we have these cluster of Envoy nodes that can horizontally scale. And then now we could dedicate these clusters to like staging environment, to like production environment, to our build systems, et cetera, et cetera. So that helps minimize some of this like single point of failure issues that we described earlier. Finally, some bonus side effects that we realized as part of this project. It was a forcing function to upgrade a lot of deprecated libraries or old libraries. So for example, Bodo doesn't really behave nicely with Egress Proxies, so we upgraded Bodo 3. Other teams are now using the same information, so our infrastructure teams can answer like, who's using DynamoDB, who's using S3. It's enforced best practices. We've seen people attempt to mutate production workloads and by downloading arbitrary things. So we prevented that. And there's also finally this flywheel effect. There's additional rich telemetry for incident response for our detection team to write alerts and rules based on this data. Cool. This is my contact information. LinkedIn is the only social media that I have. Feel free to message me there. I'm more than happy to answer questions. I've written about this topic before too, so if you like a written format essentially of this talk, it's there. You can search for it. It's also linked in my LinkedIn bio there. Cool. Thank you.
Thank you so much, Dean. All right, we have time for a couple questions before we wrap. If you have questions, I'm going to come to you. I see one in the back here on your left.
Thank you for the talk. So how do you deal with the service owners putting stars in the access lists?
Oh yeah, so Envoy does support wildcards, right? Yes, so security does do a review of it, and sometimes, yes, if it's really overly permissive, then we like, hey, can you please explicitly specify the domain that is allowed? But so right now, people create PRs for it in GitHub to update allow list, but we're actually building an additional control plane that would help enforce and help prevent that type of overly permissive definition. Yeah.
Next question is going to be up here on your left.
Do you also filter traffic going to, let's say, ChatGPT, LLMs?
Directly from services, we would be able to. Like this would be fully
Looking at
capable to
payload?
it. Not at the payload level. No, this wouldn't have the observability at payloads.
Thank you.
Yeah.
Next question's from the middle of the audience.
So you talked about how the catch-all proxy is using an Envoy sidecar. So
Yes.
do you have any capability to prevent malicious traffic that wouldn't be coming from something running in Kubernetes?
So you mean like if someone was attempting to reach the sidecar directly?
If something is trying to egress, but it's not running on a Kubernetes node, right? Because the Envoy proxy is attached to the node, correct?
Right. Oh, so he's like, if someone tries to go through the egress proxy without first traversing through, or
So you have malicious code that's running in your environment somewhere, but it's not on a service. Do you have capability to
Got it.
catch that?
Okay. Yes. So yeah, I mentioned that a little bit earlier, but this drives into like the topic of like service to service authentication, right? You need the workloads to be able to test their identity through the internet gateway itself. We do have methods to do this. I didn't have enough time to talk about it, but find me afterwards and I could talk about it a little bit more. But yes, we do have like strong identity attestation and workloads. Yeah.
One more round of applause for Dean.
Thank you.